Okay, so we're going to cover some basics of probability today, what probability is, and some basic notation especially, and some rules, including conditional probability, which is a new concept probably, but something that hopefully by the end of the class you'll find fairly intuitive and understandable, something I really want you to get what it means. I'm going to put all of this into the context of screening tests. There are plenty of other applications for probability, but this is probably the most important one for public health, and one that's important, I think, also for the general public, because many people, almost everyone, is going to have screening tests done to them at some point. And if you understand a bit of probability, you'll know what's behind those tests, and you'll know that you know that they're imperfect, but you'll know how they're imperfect and how they're being applied in your situation. And I'm going to cover Bayes' theorem and its application to screening tests. And that is, there's going to be a little bit of math there, but I'm going to make it as easy as possible for you to apply Bayes' theorem. So let's start out with an example of a screening test for cancer. Now, let's say we have a screening test that is correctly positive for 100% of cancer patients. So that means that if you have cancer and you take this test, it will confirm that you have cancer. And let's also suppose that the prevalence of this particular kind of cancer is 5 per 100,000 people per year. So if we take that test and apply it to this population where the prevalence is 5 per 1,000, what is going to be the probability of individuals in that population testing positive for cancer? Do you have any guesses? And I'll take guesses from the audience as well, or thoughts about answering this question. So we take this test that always returns positive for someone who has cancer and apply it to the general population. So suppose you're a member of the general population and you get this test and it says positive. How worried are you? You're very worried, right? Well, the consensus from the audience here, for those who are online, is very worried. But there's a bit of a trick to this question, and the trick to it is that I haven't given you enough information to say how worried you should be. You can't tell from this information because it depends on what its performance in people without cancer is. So in the trivial case, suppose this is a test that is so sensitive that it just always says you have cancer. In that case, you would have only a 5 in 1,000 chance, or the same as anybody else in the population, of actually having cancer. So before you get too worried about it, you should want to know just what the performance of this test is in healthy people. So, so the lesson there is that the performance of a screening test in the general population depends not only on what it does for people with the disease, it depends on what it does for people without the disease as well. And we're going to cover that in a lot of detail today. And hopefully this is something that by the end of the day and end of the next assignment you'll really grasp. Do you believe me? Yeah, you know, if the test is just a sheet of paper that says yes all the time, then it's not giving any information. So I'm going to answer Daniela Steffen's question online, or comment, who says you can't tell with the data provided, and that is correct. Okay, this Q&A thing works. So Oh, I need to get there. Okay. Sorry, let's get to the next slide. Okay. So a second example, and this is an example from the handout that I gave you. I don't know if you had a chance to read it. If not, that's fine. But if you didn't, I would suggest you read it after the class, because it will help to give you some context for why this is important, and help give you some intuitive, non-mathematical understanding of these concepts. But the example is a screening test for chlamydia. And this is a screening test that's being applied in two different settings, in a sexually transmitted disease clinic, which we would call a sexually transmitted infection clinic now, where the prevalence in the population that enters that clinic is 30%. And then in a different setting, a private practice, where the prevalence of chlamydia of all the people coming in for the test is 3%. Okay? And then it divides up the performance of the test among those who are positive for chlamydia and those who are negative, and shows the number of positive and negative results in those two populations. So on the left-hand side here, as an example, so we have 300 individuals, 30% of the population, who are positive for the disease, and out of those, 294 test positive. So this is almost that case where if you have the infection, it almost certainly will tell you that you have it. But then you see among these negative cases here, it's actually pretty discriminative. Among those negative cases, only 21 of them tested positive out of 700. And it goes through the calculation of something called positive, or they call it predictive value positive. I usually call it positive predictive value. And I'm gonna define that for you later. But the important thing is, so positive predictive value, I'll tell you, give you a preview now. Positive predictive value is something that you're probably most interested in as a patient. That is, if the test tells you that you have the infection or the disease, what is the probability that you actually have it? So you notice that that's kind of subtly distinct from what I asked from the information I gave you at first, which was, if you have the disease, what's the probability that the test tells you you have it? Instead, this is, okay, the test tells you you have it, what's the probability that you actually do? And the thing that this article is pointing out here and emphasizing is that that depends on the population and on the prevalence in the population. Any questions before I move on? And I am going to define this much more carefully. This is just a motivating example to tell you why we're doing what we're doing. Okay. And thank you, Vanya, for saying that the sound is much better now without the background sound. I figured out what was causing that. I'm just going to clear a few of the comments that don't need to be answered. Okay. Okay, so now you have some background. I'm going to give you some definitions that you need to understand for probability and its application. So the individual tangible thing that we are really interested in is called an event, and that is a measurable, definite outcome. So this is something where, say, an individual has a chlamydia infection, yes or no. So there's not, at that point, you know what the answer is. Individual survives past 70 years of age, yes or no. At least if they are older than 70. Or an infant survives the first year of life, yes or no. So these are individual events, something about one person and where there is a distinct outcome. In these cases, it is binary. And then a probability is the rate of that event over a large population. So the probability of getting chlamydia as a percent or a fraction, so the fraction of people in a population with chlamydia, or the probability of surviving past 70 years of an infant surviving past the first year. So the distinction event is one thing, probability is how often that thing happens over a large population. All right? So screening tests. Sensitivity and specificity are important intrinsic properties of that test. It has to do with how that test performs both on individuals with the disease or infection, that's the sensitivity, and its performance on individuals without the disease, that's specificity. So in that first example, where if you have cancer, you have 100% of getting a yes, that meant 100% specificity. But the key information that I didn't give you was specificity, which is if you get a negative, what is the probability of a negative test for people who do not have the disease? So in that case, if you give that same test to people who do not have cancer, and it always says they have cancer, then that is 0% specificity and it's a useless test. Okay. Sensitivity and specificity are important, so I'm going to go through a detailed example about them. So type 2 diabetes mellitus. This is not something that I've studied myself, but it is highly prevalent, especially in older and obese Americans. The gold standard for this test, and we call it gold standard because it is the best, the most accurate way we have of determining whether someone has diabetes, is this oral glucose tolerance test. So we're going to take the outcome of this gold standard test as the truth. The screening test, on the other hand, this fasting plasma glucose, it's easier, it's faster, it's convenient, it's cheap. So the gold standard is not something that could be given to the general population or even a high-risk population, but the screening test is. It's something that's sort of quick and easy enough that you could give it to lots and lots of people. And of course, screening tests are available for all sorts of conditions, as you know. So let's suppose that we're testing we're trying out this test for the first time in a clinical trial. And for this clinical trial, we've recruited 40 volunteers. And these volunteers have all been given the gold standard test, and we've determined that 20 of them are diabetics and 20 of them are non-diabetics. So this is not representative of the prevalence in the whole population. They are recruited so that we'll have equal numbers of diabetics and non-diabetics. Now, this plasma glucose test might look something like these measurements. So each dot here is one measurement on an individual. These are high, these are low. And here are the diabetics and the non-diabetics. And this is an example of a not great test, something that will help give you some indication of whether someone has the disease, but is not highly accurate, because you can see up here at sort of the high blood glucose, so that's a continuous measure, The people with highest are diabetics, but they're non-diabetics with pretty high blood glucose as well. But you can kind of see in this dot plot here that among the diabetics, generally it's higher than in the non-diabetics. So that's what makes this a potentially useful test. Now, in order to use the test, we're probably going to have to set a threshold. We need to decide whether we think someone has diabetes or not. And so to do that, we set a threshold. This is something very common to a lot of tests. It's not, the laboratory itself is probably not a binary outcome. It gives you something continuous like fasting glucose level, and you have to set a cut point. So here's one example of a way to set a cut point. Down here, a fairly low threshold. So this cut point is going to tell you that lots of people have diabetes. And this plot here, you can see, is summarized in this little 2x2 table, and you'll be using 2x2 tables like this a fair bit. This is usually the way you would analyze such a problem, and it's just a count of the number of people in each of these boxes. So remember the columns, this is our gold standard, whether people have diabetes or not, and then the rows are what the test says, which a test positive or negative. Make sense so far? Okay. Any questions from online? I don't see any questions. So here's another way that you might set the threshold. You could set a high threshold. So now you're not going to say that very many people have diabetes. So by setting this, you say fewer people have diabetes, and you're better at those predictions. So someone who has a positive test is more likely to have diabetes. And this is what you're seeing in the bottom right here is what we call the sensitivity specificity trade-off. So back on the previous slide with the low threshold, we had 85% sensitivity, 30% specificity. Now with the high threshold, we go down to 25% sensitivity. We're only catching 25% of the people who actually have diabetes, but our specificity is up to 90%. So if we say that someone does not have diabetes, there's a 90% chance that they do not have diabetes. So by moving that threshold up and down, you can adjust that sensitivity specificity trade-off.
What threshold you can use?
Okay, the question from the audience. Paulette, I'll get to your question in a moment. Question from the audience is what determines the threshold that you use? And the answer is it's complicated, and it depends on the trade-offs in your public health setting, on what the consequences of missing someone who has the disease, or what the consequences are of incorrectly saying that someone has the disease. I'll talk a little bit about that later, but there's no really good answer to that, because there are trade-offs no matter where you set it. Okay, answering Paulette's question, the significance again of the height. So the height, which is this line here, this is the threshold that we're setting on the results of a lab test that gives a continuous result. So the continuous result here is fasting plasma glucose. And it varies continuously between high and low, but we have to set a threshold somewhere between between a positive test and a negative test. So the significance of the height is where we say that the test is positive for diabetes and where it is negative.
Mm-hmm.
Okay. So this example is nice because we can see let's see. I have another question from the audience. Sorry, I don't understand your question, Vanya. It was in the article, too many variables. You'll have to clarify if you want me to answer something there. Oh, I think that probably was a reference to the question of how do you select the threshold? And in the article, they say there are a lot of factors that enter into that consideration. Okay, so here in this example, we know who the diabetics are, who the non-diabetics are. But in a population coming into the clinic, there's no lines separating them. And they're all mixed together. So it's, we have to, only in a trial where we've done the gold standard would we actually know who really has diabetes and who does not. And of course, actually, there's no color and no label either. All we have is this threshold for the test that we have set previously based on some clinical trial. And then as new patients come in, if their test comes out above that threshold, it's a positive test. If it comes out below the threshold, it's a negative test. We no longer have the answer. So the high set point there, it identified 7 subjects as having diabetes. In the low cut point, it identifies 31 subjects as having diabetes. But of course, now we're just relying on prior information to estimate what proportion of those are correct. So to summarize sensitivity and specificity, lab tests often give some continuous measure, and we have to choose a cut point on that measure as to what constitutes a positive test. And different cut points will yield different sensitivities and specificities, and there's a trade-off between them. You can increase one at the cost of decreasing the other. And of course, that cut point determines how many subjects you are going to say have the disease as a result of a positive test. Okay. And so I guess I didn't put this in the notes, but just to go back to the earlier question of how do you set the threshold, and to summarize, it is going to be a judgment call and a cost-benefit analysis based on what the impacts of mistakes are going to be. So if it's something where the ramifications of missing someone who has the disease and not catching it with your test, then you probably will, if those ramifications are very, very high, then you probably will set the threshold low. If on the other hand, the risk of missing someone is not so high, and the result of a positive test could be, invasive tests, things that are harmful in themselves, then you will probably want to set the threshold higher so that you don't have too many cases that you call negative or call positive but are in fact do not have the disease. Make sense? Yes, question from the audience.
How does the reliability of a test impact the sensitivity and specificity we are talking about? Yes, reliability. How does that affect?
Okay, so the question is how test reliability affects sensitivity and specificity. So for a given test that is fixed, the test is what it is, you can only trade off between sensitivity and specificity. But if you have a more reliable test, you develop a better laboratory technique, a test that is somehow physically different and better, so that separation that you saw on the previous slides is greater, and I'll go back so that, you know, the separation here between the diabetics and the non-diabetics is greater. Only by having that more reliable test, you can increase both sensitivity and specificity. And that actually often, for researchers, we will look at an entire range of sensitivity and specificity, or we'll look at one certain specificity that we're looking for, and then say how reliable the test is according to what its specificity is at a given sensitivity, and keep on tweaking things until we maximize both sensitivity and specificity in the range we're interested in. Another question?
So the sensitivity and specificity, is that like a measure of how reliable the test is?
Yes, they're part of what constitutes the total reliability of a test. So the reliability I would describe as being how well it separates your cases from your controls. The sensitivity is its performance on people with the disease, and the specificity is performance on people without the disease.
Which one is without?
Sorry?
Which one is one without?
Specificity is the performance on people without the disease. I'll just back up there. So in this case, the specificity, it's the fraction among the non-diabetics who have a negative test. So if you can keep this plot in mind, just remember that the sensitivity is the left column and the specificity is the right column. And the overall reliability of the test is how different these two distributions are. And there are different ways of measuring that. Okay, Alex B is saying that reliability equals repeatability. So, as in, if you give the same person the test twice, do you get the same result twice? And that's a fair definition of reliability. Also, I guess in my research, I tend to think of that as reproducibility, and of reliability as being like its discrimination power. The terms I actually use are discrimination and reproducibility or replicatability. Okay. So recall from those slides, sensitivity and specificity are properties that are intrinsic to a test. So a given test, a given laboratory procedure, and a certain threshold will have a fixed sensitivity and specificity. It's not a function of the population that you apply them to. Positive predictive value and negative predictive value, however, these are the things that are of greatest interest to the person receiving the test and to their doctor, and they depend not only on the properties of the test, but they depend on the population that they are applied to. So positive predictive value, that's the probability that someone with a positive test has the disease. So in that early example of the cancer screening test, if the positive predictive value is high and you receive a positive test, then you should be worried. But you need to know the positive predictive value in order to know how worried you should be. Okay, and then negative predictive value is the same thing, but you're predicting not having the disease. So a test with a high negative predictive value if you get back a negative result, then you can rest easy and be confident that you do not have the disease. If it has a low negative predictive value, then a negative test doesn't mean too much. So do those ideas make sense? And you can see that those are really the things that matter for how useful a screening test is. Going back to this diabetes example, I told you before that sensitivity and specificity are the columns. Well, PPV and NPV, those are the rows. So, so here was a calculation of sensitivity and specificity. Here's the calculation of PPV and NPV. So positive predictive value, you take all the people who received a positive test and say what proportion of them in fact have the disease. And in this case, it's 5 out of 7. And the negative predictive value out of the people who receive a negative test, what's the probability that they're negative? And I made a mistake here. Can anyone see the mistake? Yeah, let me see. Okay, so yeah, this. See if I can. I can't get this to work. Anyways, please take your notes and note that should be 18 out of 33 because it's among the people with a negative test, what's the probability that they in fact do not have diabetes? It's 18 out of 33. Yes, Alex B, you're right, it's 18 out of 33 is the negative predictive value in this example. So you can see again here by looking at this example, if you go to a different population where the prevalence of diabetics and non-diabetics is different, you are going to shift people. Say we go to a lower prevalence population, you're going to shift people from the left to the right. And that's not going to change your sensitivity and specificity, but it is going to change your PPV and your NPV because you're going to be taking people out of the left-hand column and moving them into the right-hand column. So as you go to a lower prevalence population, you are going to reduce the PPV and increase the NPV. Let's see, Paulette says should total 40. I believe that among the PPV and the NPV, the totals are 7 and 33. The total number of people in this study is 40, but keep in mind that these calculations, PPV is done only among the people with a positive test, and NPV is among only the people with a negative test. So it's not the entire population. It's just the part who received a positive or negative test. This feature that PPV depends on the population it's being applied to has caused great debate and confusion in the literature. So if you can understand PPV and the fact that it depends on prevalence in the population, you will be far ahead in interpreting the results of screening tests compared to most people, including a lot of researchers. There have been publications in the past that took a case control study with equal numbers of cases and controls, calculated the PPV, and then directly applied that to what the PPV would be in a target general population. And as you know now, that will be grossly incorrect because the prevalence is so different. So you need to make a correction. You can take your clinical trial, your case control study, estimate the sensitivity and specificity of a test, but then when you go to see what its performance is going to be in the general population, you're going to have to use Bayes' rule to make an estimate of the PPV in the general population. I'm going to show you how to do that. I'll both give you a formula and I'm going to give you a web tool so that you can do it without a formula in the future. But it's a small formula and you can do it.